So, uh, good morning to all. Today, let us uh, talk about the sequence modeling. Especially in sequence modeling, I'll go a little in detail about the recurrent neural networks and briefly tell you about, I'll not go into the details of the LSTM network. Then subsequently, I'll take you to the TDNN, that is time delay neural network, which will go a little in detail to understand the basic architecture of that TDNN, because this is what essentially we'll be using for our Kaldi based speech recognition. But nevertheless, having said that, even RNN based systems are also used to build the speech recognition in two different aspects. Like, say, suppose we take end-to-end speech recognition system, especially deep speech. So the backbone of the deep speech is all about building the network using this RNN. Whereas even in language model, so this recurrent neural network is also used as a backbone algorithm when we build the ASR. So then subsequently we'll go through the TDN. So I'll take you through this presentation, and the books I've referred to prepare this presentation. You can note down, and just not only confined to this topic, but if at all you people are interested to know more about this deep learning, in fact, like, we have to start with the artificial neural networks. One of the fundamental books, so well written, and it's worth referring, is Artificial Neural Networks by B. Yagnanarayana. That is one book. And equally sound basic fundamental book is Neural Networks, a Comprehensive Foundation by Simon Hyken, is another book worth looking at it. So these two books, apart from that, there is one more book called as, one more book on fundamental artificial neural networks by Fawcett is also worth looking at it. So they would have dealt all the required basic fundamentals that we need, so that we learn deep learning in a more effective manner. So better we go through those three books. Like, it lays down the mathematical and also the algorithmic foundation that is essential before we learn the deep learning. And one more book, that is Neural Networks and Deep Learning by Charu C. Agarwal, is also a good book. Like, there's a book which has linked the old literature with that of the new. So in a sense, he started with the artificial neural networks, and then slowly he has linked to the current day deep learning algorithms. So this is one more book. And what best, like, if we can listen, we can read from the very people who propose these algorithms. So such one book is Deep Learning by Ian Goodfellow, Yoshia Wengio, is also a very good book to refer. So these are some of the books that we can refer as far as this deep learning concepts are studied. In fact, I've taken one chapter from this Charu C. Agarwal for this presentation. Then, apart from that, there are a good number of resources that are there in the internet, and it makes our understanding easier, pictorially, visually, very appealingly. They do represent the concepts. So you people can refer some of these links as well. So one such link is the deep learning series of lectures from MIT. So that is one good link to refer. And Simply Learn is also one good link to refer. Analytics Vidya. So likewise, I've referred some of the web content while I prepared this particular talk. You people can refer to these links as well. I'll share the slides and also the links. You people can refer for detailed studies of these topics. Now, let us come to the sequence modeling. So all this while, of course, starting from Umesh sir, so Samudra Vijay sir, and also Prasanna sir, have dealt with various kinds of algorithms. So wherein you people have come across both types, be it like sequential or non-sequential type of data. So wherein we do apply certain algorithms which suits that kind of data and derive a certain outcome from those networks. Outcome could be the classification problem, regression problem, or a synthesis problem, or conversion from one form to another form. So all such problems can be solved using these powerful deep learning algorithms. So if we come to specific to the sequence modeling, let us imagine, like, if we do have a dot on, say, plain background, and if I ask you what would be the trajectory of this point, if at all it's dynamic in its nature, so in what direction it would move. So without any data prior to this, it can be any of those 360-degree plane, a 2D plane, or if we do allow one more axis as its independent variable, so ball can also come out of the screen or jump below the screen, right? Yeah. So anywhere. So in a spherical sense, like the point can move anywhere across, basically. So that becomes a quite a difficult answer if at all somebody poses me, like, what would be the trajectory of this point and in what direction it could move in, say, 5 seconds from now, 2 seconds from now. So that is the inherent problem if we don't have the past history for this particular point. So if we don't have past history, we can't even predict, like, what would be the future course of action this point would be taking. So that's the dilemma that we have if at all we don't have the past history. Now, how will I predict it? As I said, like, we do require past history for this particular point. Say, for instance, if these points are provided by someone, and this is how the point has come to this specific time point, and there are few data points that I have from the past history. So looking at these, certainly I can predict what would be the next outcome or the next point, next point where it lies, basically. Yeah, it's quite easy if I have this past data. And such types of data are called as sequential data. And if we do have that sequence information, we can predict, like, what would be the future course of that particular point, or it could be any data for that matter. For example, in general, the neural architectures are inherently multidimensional, designed for multidimensional data. So that's what you people saw through in the previous lecture. Most of the fully connected network do handle multidimensional data. So we do feed the multidimensional data. And one inherent assumption that we make when we deal with the generic fully connected networks, MLP or any such networks, one inherent assumption that we are making is all those data points are independent from each other. So that's a too far-fetched an assumption for certain kinds of data, though that might be valid for some types of data, but largely to say with we cannot generalize that particular point. So data will not be independent to each other. Say, for example, the typical data that we deal in case of speech, audio, video, text, or it could be biological data, right? They're all sequential data, and there's a sequential dependencies, basically. So when I say what do we mean by sequential dependency, for example, the current sample is dependent on past few samples in case of speech or audio, right? Likewise, in case of video, the current frame of video is dependent on past few frames of data, right? So likewise, text, when I am typing a sentence or speaking a sentence, so words cannot be independent entities. So they have to be connected in a sequential form to derive certain semantical to derive certain semantics out of the sentence. So henceforth, there is a large dependency from the past few samples as far as these kinds of data are concerned. So such kind of data are highly sequential in nature, and they are highly dependent on past as well as future samples, future data points. So this is one attribute with reference to the sequence based data, and the kind of modeling techniques that are suitable to handle such kind of sequential data are called as sequence modeling. So that's what we'll be keen, and that's what we'll try to understand in this particular session. How do we handle such kind of a challenge using neural network? Yeah, coming to time series data. So there are many types of time series data that we come across practically. So we'll see one by one what do we mean by time series data, and what are the practical examples for this time series data we have at hand. So in a time series data set, the value on successive timestamps are closely related to one another. In a sense, it is highly dependent on adjacent past few and maybe post few samples. So that kind of data sets are the time series data. So if one uses the value of these timestamps as independent features, of course, it is an independent variable. The time is an independent variable. Then the key information about the relationships among the values of these timestamp is lost if we make this assumption that the time axis is independent from each other. Then that's a big assumption as far as these kind of data is concerned. So that may not be a valid assumption when we want to deal such kind of data, basically. So for example, the speech. So if at all I'm uttering certain phoneme sounds, so again, those phoneme sounds are highly dependent on what subword I'm trying to construct in my production mechanism. Likewise, connect those subwords to form words, right? So then connect those words to form sentences. So connect those sentences to form paragraph. So likewise, there is a huge amount of temporal dependencies on these kind of data that we deal with. So henceforth, if we do make that assumption of independence with reference to time axis, then that's a great deal, and we may lose a lot of information as far as this data is concerned. Even if we go on to build such kind of models, that may not be so accurate models to address the given problem that we've taken up. So again, coming to textual data, though it doesn't come under the category of time series data, nevertheless, there is adherence of some notional time with reference to these textual data. So strictly, it is not time in seconds as we know, but certainly there are positional dependencies as far as this textual data is concerned. So for example, the current word is dependent on past few words and also the post few words. And also it could be altogether a sentence. Then we also may type an entire paragraph. So everything has to be related, and they should be in coherence, right? So if at all it's incoherent, understanding the message for we humans becomes so difficult. So if I just talk gibberly and talk like all the bag of words to you, so it doesn't make any sense. So we people find it difficult to understand the interpretation or the underlying meaning of that particular sentence or a paragraph. So that's where there are a lot of dependencies as far as these types of data is concerned, right? So yeah, one can obtain a better semantic insights if we have that notion of time or positional information with this. And in such cases, it is important to construct models that take the sequencing information into account. So somehow we need to tailor make our models so that like it can handle these sequence information. Somehow if we can embed this sequence information to the network and go on to build the network, we can hopefully meet the kind of challenges this kind of data has, basically. So one of the most common types of networks which handles these kind of text data or time series data are called as recurrent neural networks. So that's what we'll try to figure out, how this recurrent neural networks helps us to handle these kind of sequential data. So that's what we'll spend some time on it to understand what is the inherent concepts of these recurrent neural networks. So some of the applications as far as this recurrent neural network is concerned, I'm sure like many of us or most of us would have used and had taken the benefit of this recurrent neural network already. I'll tell you a couple of examples. Already we've been using this recurrent neural network in our day-to-day life. So coming to this recurrent neural network, the general architecture is that the expectation is that we feed some or the other form of a time sequential data as an input to the network, and network processes this data, and as an outcome, it could be again a sequence of output. Say, for example, in our case of speech recognition, we can feed the features as an input. So either those features could be the frequency-based features, say in the form of spectrogram or Mel frequency cepstral coefficients, or it could be simple time sequential data itself, raw speech signal itself. So we can feed such input data to this network, and if at all this model is trained to decipher the message that is there in the signal, then the outcome of this particular neural network could be the sentence itself. So in a sense, this neural network would have converted whatever be the form of the data to its corresponding sentence in the textual form. So that's what is desired when we take speech recognition. Right, and to an extent, even Google makes use of this kind of models, especially when it comes to wake up words. So it could be some sort of wake up words that are there. Say, for example, in case of Amazon Alexa, Alexa is a wake up word. So usually these kind of networks are used in such kind of wake up scenarios, which is called as keyword spotting. So we can implement those and then decipher like what one has spoken, basically. And then one more application could be the translation. So here in the picture, it depicts like the speech-to-speech translation. For example, I can give input in the form of speech in one of the languages that I know, and if I want to communicate the same in other foreign languages, the correspondence can be built using this recurrent neural networks. So it helps us to directly translate the spoken sentences in one of the languages to another language which I may not be knowing. So this comes in handy, and such kind of speech translators are there, are existing in the market, but they may not be as popular as automatic speech recognition. So for example, China, China, they have a tool. So any people who do visit China, they often find it difficult to converse in the local language if they don't know it. So then often even very life mundane tasks become so difficult in such kind of alien language environment. So that's where this speech translation comes into rescue, and recurrent neural network can be utilized for this purpose. So it helps us to convert that speech directly. So not only in the spoken form, but they can also help us in the textual form. So the textual form of translation is called as machine translation in NLP terms. So this, you feed text in one of the languages, known languages, and it helps us translate with reference to the correspondence to other foreign languages. So such a block is called as machine translation. So likewise, as I said, like already you people have been using this this service of recurrent neural networks. So in the form of Google applications, be it in your Gmail or Google search, you might have noticed as soon as you type a couple of words, it starts recommending the words. It starts putting the words in our mind, basically. So who helps that, and what kind of network sits beneath this? It's the recurrent neural network. They try to gather the words that we have typed, and it would have learned from the from lot of data that the Google has from that context, it learns what could be the word the user is anticipating to type with, right? So that's what these algorithms tries to find out, and most of the times they're correct also. I mean, I've not measured it, but safely we can say 70 to 80% of the times the prediction is correct. And so, for example, one such example is, suppose if you type LAS as a word in the Google search, already it starts giving the recommendations as San Francisco, Vegas, right? So there are many recommendations that are given by this Google search, or even mail when we type, basically. So it almost auto completes the search, and within no time it gives the kind of recommendation, and most of the times it is true as well. So that is the ease at which we can train the models, and we can think of quite a complicated applications which were not so feasible even 3-4 years back have become a possibility, have become even commercial possibility. Forget about in the labs, they're all deployed in the commercial market. So likewise, another type of application could be given image, and if you ask humans to describe the image, so he can come up with many such descriptions. Say, for example, in case of first image, you can notice that there is a dog trying to jump, and there's a ball basically, and at the background there's a building. There could be water flowing, and all such descriptions can be made. And even we have that innate ability to build a story out of a given image, right? So such is the wealth of information that is there in the given image. Now, the same if we have to expect it from the machine. So then how we would build the algorithms for that. So one such best fit case is the recurrent neural networks. So you feed the image as an input, and recurrent neural network will be able to give out the descriptions in terms of independent words, or they could be connected words in the form of a textual sentence, or even it can go on to describe 2-3 sentences about the same image, right? So that's the kind of strength and the kind of applications that we can build using these recurrent neural networks. So now, even before getting into the architectural details of this recurrent neural network, let's get to know in what form this sequential data is represented when we do want to handle such kind of sequential data. So coming to the sequential types of data, generally speaking, there are two broad types of representing this particular sequential data. One is called as the real valued, another one is called as the symbolic representation. So let's try to understand what we mean by the real valued sequence data is, and symbolic sequence data is all about. So real valued sequences are also referred to as the time series data. So in practical applications, the symbolic values is more common. I mean, you can come more common than the time series data. Nevertheless, there are large number of time series data as well. So can you give some examples for time series data that you practically have come across? I'll give you a clue. Speech is one such time series data. So any other types of time series data that you've come across? Already in the presentation, I've quoted few applications.
Yeah, stock market prediction.
Yeah, stock market prediction, or a currency value changes that we can, it could be Indian rupee, American currency, so whatnot, right? So it could be biomedical data, it could be DNA, genetic sequence. So you name, like, they're all time series data basically. So, and there are certain symbolic representation of this sequence data as well. So for example, video sequence, or it could be textual data, right? So they're all symbolic representation of the sequence data. So now, we have seen through the conventional network all this while. We know what is the structure of this conventional fully connected network is all about. Say, for example, if we take up, let's say, a sentence, analytics is hardly any run. So I mean, hardly any fun. Sorry. Yeah. So that is the sentence that we have. And likewise, there's one more sentence. Let us say analytics must be fun. Right. So these are the two sentences. If you just look at the number of words, more or less they're common, except for is and be and any. Majority of the words are quite common across these two sentences, but there's a difference. Analytics is hardly any fun, right? Which is a negative connotation as far as the sentence is concerned, whereas analytics must be fun, right? So which looks to be a very positive sentence. So though the number of words are same, the sequential ordering of these words are quite different, and the meaning it conveys is also totally different. And if we try to feed such kind of two different sentences to this kind of fully connected network, hardly they'll be able to interpret the difference between the two sentences. Why? Because the inherent structure of the fully connected network is such that it considers all the input data points. Like here in this case, it is words. It could be time, in case of time series data, in case of speech, like they could be raw values, real values of the speech samples. But try to feed such input samples to this kind of fully connected network. They try to treat them independently, and they don't try to decipher the relationship between one word to next word. They don't derive the relationship. So that's one of the major problems of these fully connected network when we want to try and handle these kind of sequence data. So that's where these kind of networks fail, and they won't be able to give us the right output also. That's one of the problems. That is one problem. Apart from that, if you can just notice this, one of the sentence has 5 words, whereas another sentence has only 4 words. Now, what should I do as far as the 5th word is concerned? Yeah, there are mechanisms of zero padding and other things. That's fine. That's fine to handle if the spoken sentence is of few words. But what if, like, if I want to handle a sentence, if I want to handle a big sentence, if I want to handle the paragraph, if I want to handle the entire document? So how long I can keep increasing the input node, right? So that's one of the major difficulties to handle this kind of data. So I mean, my input nodes are finite, and I cannot simply go on increasing the number of input nodes. So that becomes quite difficult to handle. That is one thing, and there's no limit to it, right? So that's one of the major difficulties that we have as far as these conventional fully connected networks are concerned. So henceforth, these kind of networks are not suitable to handle the sequential data. Yeah, so these are the two challenges that we have, as I said. So the input data is of variable lengths, right? That is one thing. And moreover, the network architecture is such that they don't derive the relationship between the sequential form of the data. So these are the two major difficulties that we have if at all we want to deal this kind of sequence data. Yeah. So then how do we handle that? Of course, we can sort of handle using the fully connected networks. People have come up with the solutions in the literature. Like, say, for example, I can handle the textual data in the form of a bag of words. So put all those words in a bag and ignore the temporal dependency or the sequential dependency of the data, and just deal it as a bag of words. That's fine. That's fine as far as some kind of analysis is concerned, but may not hold good for many scenarios. Say, for example, if prime minister speaks in an election rally, so people do tend to get the words from his speech basically, and generate word plots. I just forgot the name of that. What do they call that as? So we do generate the word plot, like so how many words he has spoken, and based on the frequency of occurrence, we give different size of representation of those words in the plot. Basically, that tells like what were the major words and how frequently is used, and that kind of information. But if I want to find out the inherent meaning of the speech, right? So what has he spoken about? right? If I want to understand what has he spoken. So we humans can understand that quite at ease, but now the difficulty is how do we make a machine understand, right, what he has spoken. So that's where if we treat such kind of problems as a bag of words, so literal meaning is take those words of the sentence and put them in a bag and feed it to the network. I mean, that's as literal as that. So once we take those words and put them in a bag, that temporal sequencing of the data is lost basically. So that's one of the difficulties. Let's try to overcome those things. And one more problem, for example, sorry, let's take this sentence that is the cat chased the mouse. It's quite common, and there's no big surprise in that particular sentence. Whereas see the other one, the mouse chased the cat. If you just look at the words in both first sentence and second sentence, words are literally same. There's no difference as far as the words are concerned. The only difference is when are they sequenced, which one comes first, right? So that puts in a lot of semantic meaning for a given sentence. If that itself is lost, like in case of bag of words, then there is no point in finding the meaning of that particular sentence. Second sentence is quite a surprise, and rarely does that happen, and entropy is quite high in the case of second sentence compared to the first one. So these are certain things that the conventional networks cannot handle. So in fact, like we do need a sophisticated network to handle this sort of linguistic intelligence. So how do we do that? Like is what we'll bother about. Like, yeah. So then how do we resolve this this kind of problem? So it is important for us to build a network such that it somehow encodes this temporal dependent information onto the network itself. So how do we design such an architecture is the challenge at hand. The goal of such an approach would be to, of course, I mean, I cannot have infinite parameters, so I should have finite parameters. After all, I need to practically realize this network and build some applications. So in that case, the number of parameter requirements should also be quite limited when we build such an architecture. I cannot utilize large number of parameters. Yeah, so such such kind of solution exists in the literature, and one of the early networks that were proposed to handle this scenario was a recurrent neural network. So let's try to understand. It has an innate ability to receive and process inputs in the order it receives, basically. So that's one of the biggest advantage that we have as far as this recurrent neural network is concerned. So the treatment of inputs at each timestamp is in a similar manner in relation to previous history of inputs, right? We require history. So based on that history, I need to derive the relation to the current sample or current word. So I need to establish that kind of relations. So in a recurrent neural network, there is a one-to-one correspondence between the layers in the network and the specific positions in the sequences. So here we'll come across the detailed aspects of this recurrent neural network. One of the biggest advantages, there's a big correspondence between the layers and the positional value of the data is concerned, be it like time series or symbolic data. So both will be correspondingly represented in the recurrent neural network. Yeah. So of course, even in textual data, we do regard them as the timestamp. It need not be in the strict sense of time, basically, like in case of speech, audio. Even in text, like we do give a notion of time, basically, though there is no inherent time that is there as far as that kind of symbolic data is concerned. So instead of variable number of inputs, that was one of the problems that we faced when we want to utilize fully connected network for handling these kind of sequential data. So whereas if length is small, if length is very large, the input nodes also keeps varying. So that's one of the biggest problem that we had in the conventional network, whereas this recurrent neural network overcomes that particular problem. Okay, the inputs are allowed to directly interact with the downstream hidden layers, depending on their positional value or positional sequence where it is placed, like basically. So it has certain relationship with the past few samples or past few words, or past few paragraphs, whatnot, like basically. So each layer uses the same set of parameters. So that's the major difference. Whereas in case of fully connected network, the weight parameters from one layer to another layer didn't had any linkage basically, and they used to get tuned independently, right? So of course using back propagation, but nevertheless there was no connection as such as far as one layer to another layer, and there was no weight dependency from one layer to another layer. They were independent. Whereas here the same weight matrix is being linked from one timestamp to another timestamp to another timestamp. So that weight matrix do get updated in a time sequential fashion. So how does that happen? We'll see. So don't worry as of now. So these are some of the fundamental differences between the conventional fully connected network and to that of a recurrent neural network. So the same layer-wise architecture is repeated. So there is exact replica of the same sequence of patterns as far as the architecture is concerned. Yeah. So, and such a repetition is called as recurrence, right? And henceforth, the name has come through as recurrent neural network. We'll see what is it. These are some of the highlights as far as this recurrent neural network is concerned. Uh, it can handle variable length sequences. That's one of the advantages. Track long-term dependencies. So for example, it could be 10-word length sentence, 100-word length sentence, or paragraph. So such long-term dependencies can be captured as far as these networks are concerned. Then it also maintains the information about the ordering of the sequence. Then it also shares the parameters across the sequence. We'll see how does that happen. So these are some of the major highlights as far as the recurrent neural network is concerned. Any questions you can ask me. You can stop and ask me. If I know, I'll answer. Else we'll discuss on that later. Then now let's see how do we convert a neural network starting from multi-layer perceptron to recurrent neural network. So why MLP? Because that's one of the early networks that we study, if at all we are dealing with deep learning, and it's easy to understand. That's the reason why we always quote this MLP or a fully connected network. So keeping that as a reference, keeping that as a basis, how do we say like what is RNNs? That's what we'll try to attempt in this case. Like, yeah. So let's say the task is to predict the next word. So let's take up one problem. With reference to that problem, we'll try to understand the network architecture as well. So given few words. So already I've been given few words. That's what our mail recommendation systems, right, or Google search would give us. Like already I have few words as far as the machine is concerned. Now what would be the next word? What would be the next prediction of word? So that's what essentially this RNN does. Let's take up that particular problem and try to understand from that perspective. Right, in the simplest form, we have an input layer, a hidden layer, and an output layer. So of course this holds good for any sort of network. It has got an input layer, it has got hidden layer, and it has got an output layer. And the same thing holds good for recurrent neural network also. The input layer is the one which actually receives the input, right? Then subsequently it is passed on to the hidden layer through some weighted connections, and they're all fully connected as far as input to hidden layer is concerned. So then from hidden layer to output layer, again, all nodes are connected to all output nodes. All hidden layer nodes are connected to all output nodes with weights, with certain weights. And the hidden layer itself consists of certain nodes, and each of those nodes are nothing but the the weighted summation block pass through some of the nonlinear activation function. So that's how we typically define one single node to be. So this is a very simplified diagram of an MLP. This is how it looks basically. We have an input, and also there is a arc that helps us to connect that input to the hidden layer, and arc has a direction, for example. Then this hidden layer eventually gets connected to the output layer, and there is an arc which again connects, which helps us connect the hidden layer to that of the output layer. And all these arcs are weighted arcs. It's not that like weight is equal to 1, so they can be of different weights basically when we try to connect these different blocks of the network. So now let's have a deeper network where multiple hidden layers are present. Let's try to complicate our problem a little. So wherein we are not just confined with one hidden layer, but we can have large number of hidden layers. That's what a deep learning multi-layer perceptron algorithm would look like. So it doesn't have one single hidden layer, but it may have multiple hidden layers. So let's try to make it a little more complicated and try to handle the recurrent neural network. So again, when it comes to these kind of multiple hidden layers, again, all these hidden layers will have activation functions, and these activations are sent to the next hidden layer, and successive activations through the layers to produce the output, and those outputs will form as an input to the next subsequent layer, and so forth and so on. That's how we do tend to build a large complicated network. Yeah, so each of these hidden layer, so they're all characterized by its own weights and biases. So generally speaking, when we do deal with the architectural diagram, so we do tend to neglect this bias. But without bias, there is no network. There is a consequence of this bias on the network, which you people must be knowing by this time. So it has weights, also bias. Bias is also fine-tuned with reference to the backpropagation algorithm. So this is how a typical deep learning architecture would look like. So in case of MLP, so it doesn't have one single layer. It consists of, let's say, 3 layers here in this case. So all 3 layers will have their own independent weight matrix, that is W1, W2, and W3. Likewise, the independent biases as far as each layer is concerned, B1, B2, and B3. So people who are not familiar with the architecture, it's not one single node, but it can have multiple nodes. All those nodes are concised as one single node here in this case. Except for that, like practically we don't have one single node, but we do have many such nodes in a given layer. And all those layers need not have uniform number of nodes. All those nodes can be of different number of nodes. And each of these layer will have nonlinear activations. So generally speaking, people do maintain the same kind of activation function as far as all the hidden layers are concerned. And I can have a different, generally I do have a different activation function as far as the output layer is concerned. So now let's try to convert this known conventional neural network architecture to a recurrent neural network. Now, how do we do that? That's the challenge at hand. Let's see that, like, how do we do? Yeah. Since each hidden layer has its own weights, and also they have their own activations, of course. Since each of those weights are independent, each of those weights are different, they behave independently. So that's one of the problems, right? As far as the sequence data is concerned. Then here the weights and bias of these hidden layers are different. Of course, it is different as I explained. Now the objective is to identify the relationship between the successive inputs. How do I establish the relationship between the one hidden layer to the next hidden layer? How do I connect those with reference to these weights? Can we actually do that? The answer is yes. That's what recurrent neural network does. Now let's try to understand how does this do basically. So Each of these layers behave independently and cannot be combined together. Of course, we cannot just take a vanilla multi-layer perceptron and just go on to modify that and to build the recurrent neural network. We need a novel way of handling these weights. So that novelty is where the recurrent neural network comes into picture here. So let's try to combine these hidden layers together. Let's try to connect them together. How do we connect them? So one means by which like we can connect these different hidden layers is through to have common set of weights and biases. When I say common, then they need not be static. So all these weights are dynamic in nature. We'll see what is the dynamics involved as far as these weights and biases is concerned when we exactly deal with the recurrent neural net. Yeah, any questions? Is it fine? Am I going in the right flow, or should I increase or decrease the pace? Any inputs?
That's fine, sir.
Okay, yeah.
Pace is okay. It is normal.
Okay, sir. Yeah, okay. Yeah. So now let's take up the same vanilla MLP and try to convert it to a recurrent neural net. So how do we do that, like basically? So take, this is the input. We do have input here as well. Of course, we'll retain that. Then these are the nodes that we had in the NLP. So let's try to retain them as it is. But internally, I do modify the structure of these node. When I say a node, it need not be one single node, it could be multiple nodes, but for the ease of our understanding, let's regard this as one single node network here. So here, if we can just see the difference between the earlier MLP and to that of this network is such that we don't have the subscripts to these weights. That is, we don't have W1, W2, W3. So if we just look at this, they're all the same weight matrix, and through this weight matrix is how these nodes are connected. They're related basically. So now a relationship is established, and no more these weights are independent. They're all dependent, right? So we have just simply took the MLP, which were of independent weights with reference to different hidden layers. Now we have tagged them together and created a relationship through this W, so that it helps us to maintain the sequential information or the sequence information basically. So since the weights are common, the same weight matrix is passed from this hidden layer to the next hidden layer to the next hidden layer. So that's where this passing of these weights is all represented by the recurrence loop. You're feeding the same weight then and now and then, like in a loop fashion. So that's where this recurrence loop comes into picture. So you can just concisely put all of them as a single node, then still do retain that input and output layer as it is, and put in a recurrence loop. The conventional MLP has been converted to the recurrent neural network. And generally speaking, this is how the recurrent neural networks are represented in the literature, or any of the material that you see with reference to this recurrent neural net. So generally speaking, this is how a recurrent neural network is represented in the literature. So there's a running loop, like you can see that you take that output and feed it as an input. So there's a recurrence loop, and there's an input node, output node, and they're all directional in nature. So they're all connected by the arcs. Again, arcs, as I said, we do retain that flavor where these arcs are weighted arcs. They're not simple one weight arc basically. So this is how we have done that. So this is the kind of typical MLP that we had. So we have taken that, we have just shrunk that hidden layers into one single node with the recurrence loop in place, and we have just transformed that MLP to recurrent neural net. So let's try to understand this structure in detail. I mean, it's little confusing. I know, like, people who have got used to this network off late or in this presentation certainly find it difficult to understand what is the inherent structure of that particular network. Let's try to understand that in a detail. So this is what we have done essentially. So there were good pictorial GIF files. This helps us to understand concepts better. That's the reason I've taken them. So from different websites, as I've referred in the early slide. So as you can notice, as we go on to build this kind of recurrent neural networks, new set of parameters are added basically. So for simplicity, let's name them as B, C, and A. So they are the weights of those arcs which are helping us to connect different nodes basically. So B is the weight which helps us to connect the input to the intermediate node, and now node has been named as H basically. And there's a repetition weight itself, or the recurrence loop weight itself, which is all represented as C. Then there is a arc which helps us to connect that H to Y. Y is the output, like basically. Yeah, generally speaking, these are the symbols that we are used to basically, especially people who deal with signal processing or image processing. We know, like, most of the systems are dealt in this fashion. We have an input which is all represented as X, and usually the system itself will be represented as H. Most of the of course, it's not a strict impulse response filter like in our image or signal, but it comes close to that. I'll tell you why. Yeah. So when we go on basically, so then there is a output layer itself. When we say at times, like, the literature may follow that Y cap to represent that it is a estimated output. It's not the actual output, and usually there is an actual output also. So which is all represented as Y, or at times, like, it is also represented by the letter D. D is called as desired output. So all those different notations and symbols you can come across while you browse through the literature. I'll just take a very short break. I'll just drink water and get back here. Meanwhile, any questions you can raise, I can answer them.
Sir.
Yes, please go ahead with the question.
Sir, in the pictorial representation, which you showed in the last slide, the entire nodes and the entire layers are merged into the single RNN network. Is it so?
Deepak will answer.
Yeah.
Questions?
Mahesh asked a question.
Mahesh, yeah, please.
Sir, in the previous slide, the entire nodes, the multiple nodes and the multiple layers boils down to single RNN network, which in turn contains the different nodes and the layers. That's what actually the previous.
Sorry. Yeah. This one is it?
Next one, sir. The animation. Yeah, this one.
Okay, yeah.
This
Yeah.
one.
See, in the earlier case of MLP, we had multiple layers, right?
Yes.
So hidden layers. So now that notion of hidden layer has been represented as one single node here. Why? Because the weights are not independent. If the weights
Yes,
were
yes.
dependent, so now we have made those weights as dependent. No more they are independent. So what I mean to say is W1 to W2, there was no relationship earlier. Now we have taken that and created a relationship.
Okay.
So that relationship is the essence of the recurrent neural network.
Okay.
That is the one which actually helps us keep track of the sequential information.
Okay.
Hope I've cleared it.
Yeah.
But to a detailed extent, we'll also go through that structure. Even to this extent, people who have got introduced to this recurrent neural net is still confusing. Let us go further into the details of it. So let's break that recurrent neural net and understand what is the inherent structure of that recurrent neural net. So if we just look at that, sorry, if I come out of the, yeah. So this is the structure basically. So if you just, I mean, what do you say? Remove that loop and just linearly represent that particular H. So this is how it looks. There is something called as X of t at the mid of that network, and there are samples to the left and there are samples to the right, basically. So which are all denoted as X of t minus 1, X of t minus 2, and so forth and so on. You can go n to the left and go m to the right, basically. So people who have dealt with signal processing, understanding this concept is not at all a problem. We know like what is the previous sequence. It is a previous time sample, which is all denoted by as denoted as X of t minus 1. So likewise, the states also inherently changes from one time step to another time step, right? Because they're all dependent weight states, basically. So that's where this H of t minus 1, H of t minus 2 comes into picture. Likewise, it need not be always causal system. So always the network need not depend on the past or present sample, but they also can depend on the future samples as well. So which are non-causal networks, basically. So but only problem with the dependence of too much future sample is what do you think, like where do you think like you come across this problem? If at all too much dependence on future samples could be a problem, where do you think like could be a problem? Past samples is fine, but future samples, depending too much on future samples, will be a problem. Where do you think like you think like there is a problem? So especially if we want to implement this in a real time, right? So in a real time, so for example, it could be cricket match, what you're watching. It could be real time speech recognition systems. So all such things. So you can afford to have some future samples, fine. Some kind of delay is fine as far as the system is concerned, but having dependence on too many future samples will be a major bottleneck as far as the real-time systems are concerned. But if you are not bothered about the real-time systems, then still you can depend as much as possible for the future as you had dependent on the past samples also. There is no restriction as such. But there's an other problem as far as the dependency is concerned with reference to the architecture itself. I'm not talking with reference to the system. The real-time system, you can't depend too many samples to the future. Yeah. So majorly, if we take this recurrent neural net, so broadly we can categorize them into 4 different types. So one-to-one network, one to many, many to one, many to many. So these are some of the types of networks you come across. So let's see the basic flavor as far as this architecture is concerned. So this is a typical single input, single output network. So this is like one-to-one correspondence. That is, you give a query. Let's say I feed an image. Basically, I feed an image. So I need to have one correspondence image as an outcome. Or you feed a word. It tries to let's say I speak one word to the network in Kannada. So if it is a dictionary recurrent neural network, it has to give me one corresponding word for the Kannada word in English, let's say. So that is one typical scenario you come across in one-to-one RNN, recurrent neural network. So this is the most simplest one as far as the architecture is concerned. Then we do have single input, multiple outputs. So I already had shown you one example. Can you give that example? Already I've shown in the presentation. Single input and multiple outputs. So you went through one of the application of that captioning of the image, right? So what is the, how many number of inputs you're feeding into the network? You're only feeding one image as an input. Whereas against which, like if I want to construct a sentence, or if I want to tell, describe the image basically. So it's not possible for me to describe in one word, right? So I need to have many words, and all those words are sequentially dependent, right? So such kind of typical networks are called a single input and multiple output network. Likewise, there could be multiple inputs and single output. Also, I've given one application scenario. Can you give that application? I've already dealt in the talk, wherein we are giving multiple inputs and expecting single output. So, for example, yeah, please.
Sentiment analysis could be one.
Yeah, right. So what happens in sentiment analysis? You feed sequence of words to the network. The objective of the recurrent neural net is to find out what sentiment it is, whether it is positive or whether it is negative. Right? It has to find out so it's a one word output. It is positive or negative, right? So this is that scenario wherein you feed multiple inputs and get single output. So likewise, you give multiple inputs and expect multiple outputs. Basically, it's many to many mapping. So this is quite easy. This is the problem that we are dealing in this current workshop. So we expect to feed speech as an input at one end and get the sequence of text output at the other end. That is many to many mapping. So likewise, it could be machine translation, text to text. It could be speech to speech. Right, altogether you can construct a different signal altogether. Need not be speech again. So you feed speech again, speech signal at one end. You can derive electroglottograph signal at the other end. So likewise, I mean, you can just keep on exploring this kind of many to many mapping as well. So fine. So this is how we saw the network in a very simplistic terms. Now let us complicate ourselves. Things are not so simple as it seems to be. Let's try to understand the inherent structure and the weights correspondence, and how do we update these weights, how do we, and what are those weights are, and let's try to understand fully. So that's what we'll try to attempt. So this is that recurrence. Let's try to expand it. As I said, the point of interest could be anywhere x of t minus 1, t minus 2, or this could be the beginning point itself. So for example, x naught. So there will be the weight xh, which helps us connect that x to the weight matrix here. So this node is all represented as W basically. Apart from W, it also has activation. For a moment, let's try to forget about that activation. So this is all represented by the W basically, or WHH. So that's how it gets represented. And then again, there is a weight which helps us connect this node, hidden layer node, to the output. So that's where this cap comes. It's a predicted output basically. So these are the three weights that we are majorly concerned, and these are the three weights that we need to adapt. And adaptation of these weights are not same as that of the fully connected network, but there's a dependency factor. So this weight first it and always like usually generally if nothing is given, we can regard this network as a left to right network. So it begins from here and subsequently goes on to this, then this, and subsequent and this one basically. So the weight WHH calculated from this first node is all carried to this basically, and again gets updated. So the same weight gets carried to this node and gets updated, and so forth and so on. So it's the same weight that is being passed from one hidden layer to the next hidden layer. So these are called as the layers basically here.
Sir, I have a query. Can you go 2 steps backwards? I mean 2 slides. Yeah, here, many to many.
Many to many.
Yeah. Sir, actually then the input time step should be equal, right? For should not be equal, right? For the machine translation. I mean the input time steps like T1, T2, T3. I assume there are 4 time steps in my input, right? For machine translation, it would be lesser or greater.
Yeah, correct. So here it need not be same number of nodes. So only for the representational purpose, it says like 333. It could be 2, it could be 3, it could be 5, it could be 10. So all such kind of mappings are quite possible in this case.
Okay. So then will this be valid even for speech translation? I mean,
yeah.
TX should not be greater than or TY. Is it so or?
No, it need not be that case. Like, I mean, input can be less and output nodes can be more. So likewise, the other way around as well. It need not be of the same length. There is no hard and fast rule. And already such attempts have been made using this recurrent neural network, wherein you feed speech as one input, like basically from one language, and you get the output of different language basically. And the length need not be one and the same. At times, like it can be smaller. At times, it can be larger, or they can be equal. So all such scenarios can be handled using this network. It's quite possible.
Okay. Actually, yes, sir, I am clear. Like I got confused with the name entity. Name entity will have equal, right? TX and TY will be equal. So I got confused over there. Yeah. Thank you.
Yeah. So now let's come to a little math of it. I'll not take too much like of your maths like here. So it's very simple. So let's decipher this particular equation. If we try to understand this equation, everything becomes easier for us like subsequently. Yeah. So coming to this recurrence relationship, so it's a time step to process a sequential data. So we know that as far as this data is concerned. Now so if we go back to this architecture, let's say X1 is my point of interest. So and only I'm dependent on the past few samples. Let's take that scenario. Let's try to avoid future samples for ease of understanding. So let's say it is dependent on a few previous samples. If so is the case, if this is HT, if this is XT, this is HT. So what would be the previous state? So we saw that network structure. Quite obviously, this will be nothing but H subscript T minus 1 basically. So at best, like this current node depends on one previous node, right? That is H of T minus 1. So the outcome of this node is a function of H of T minus 1. And apart from that, also I'm taking the input, right? So which is XT. So it is dependent. Any function I want to implement in this particular node is dependent on 2 parameters. One is HT minus 1. The other one is the XT itself. So that's what this equation says is essentially. So this is HT minus 1, which is an old state. Then we do have the input vector itself, which is XT. Then there is then these things are passed through the function, and that function is dependent on the weight. It is a parameterized function. It's not any function. It's a parameterized function, and those parameters are dependent on W basically. So W is the weight matrix which we try to update using the back propagation. So this particular equation actually helps us realize what is HT is. So what is the kind of relationship that we have created? So already we have linked this h of t minus 1 to ht. So this ht is dependent on ht minus 1. So already we have connected two different hidden layers, which were not so in the case of a multi-layer perceptron. Hope this equation has clearly made you understood how different this recurrent neural net from that of a multi-layer perceptron, right? So that's the difference. And always we deal one input at a time. We are not bothered about x of t minus 1. Why we are not bothered about x of t minus 1? We have not taken x of t minus 1 here in this case, or even x of t minus 2, x of t minus 3. I've not taken that into account in this equation. But do you think like that information is there already? If it is there,
Yes.
Who has captured it?
This hidden layers, ht minus 1.
Yeah, exactly right. H of t minus 1 already has captured the information of x of t minus 1, t minus 2, and so forth and so on, right? So depending on the internal architecture of RNN, it can withhold some temporal information back to few samples, right? So depending on what architecture we do adopt there, yeah, right? So it also has certain weightages and other things. Let's not worry about, let's try to conceptually understand this network, and then hopefully it eases our understanding for our later readings. That's the purpose of this talk, yeah. So it's now very clear. H of t is dependent on h of t minus 1, right? And x of t minus 1 and so forth and so on. So coming to this recurrent neural net, the typical recurrent neural net architecture is this, as I said, that fw, basically fw is the parameterized function. That parameterized function is nothing but this whh into ht minus 1. Whh is the current weight state, like basically multiplied by this state, that is h of t minus 1, plus wxh, which is the weight which connects the x to this node, that is wxh, and the input itself, xt. So pass them through some nonlinear activation function, tan h here in this case. So we do generally use the tan h function. So then outcome of that is nothing but our ht is all about. Now take this ht, multiply it with the weight that essentially connects the node to the output node, basically this hidden node to the output node. So where y cap t, that is the estimated output, is nothing but the why is multiplied with the ht, basically. It's now we can see they're all connected. The input, the previous state, the current w weight matrix, the weight matrix which connects x to hidden node, and the weight matrix which connects the hidden node to the output node. So all these different components are essentially connected through these three mathematical equations. Hope this part is clear. But what is this weight? What is this state? How are they, and in what fashion they are represented? We'll explore. I'll demonstrate you one example which clears all your doubts and be able to appreciate these equations. Else for it, now you know different components are connected, right? And also we have brought a nonlinear activation function into the loop, that is tan h here in this case. Generally speaking, we do deal with ReLU, softmax, sigmoid, and all other different types of activation functions. But the one nonlinear activation function used in RNN is the tan h. Okay, so now let's try to understand. Now we have got the desired output. Essentially, now how do we propagate with reference to this network? This is how that forward propagation happens in the network. So sorry, yeah.
So one doubt. So in the before slide, you had used tan h for computation of ht. So is it every time you have to use tan h, or we can use any other function like?
At least as far as I know, I think it is tan h function, but I don't know if in literature if they've used ReLU also of late. I'm not privy to that, but possibly you can use a ReLU function also, I suppose. But at least tan h is guaranteed.
Okay. Okay. Thanks.
Yeah. Yeah, so this is how this architecture looks like when we put everything in place, and when we want to introduce back propagation into the loop, this is how a typical architecture looks like. So here we have that x0, x1, x2, and xt. Basically, they're all the inputs. We know all these weights and the nodes. We know what are the prediction outputs is, and prediction outputs also do have timestamp, right, or the sequence information embedded in it. So for example, if this is my yt, then this is nothing but my yt minus 1, right? So the previous output. So previous output is also an estimated output. And correspondingly, I do have y0, right? I do have y0. If at all I do have the labels for the data, I know what is y0 is, I know what is y1 is, right? So then certainly I can calculate the error between the desired output and to that of the actual output, right? So there are different means of calculating the error. One of the simplest ways of calculating the error is the mean square error, right? So, or it could be any of those different types of errors we do have. Calculate that error, that helps us to generate that loss function. Yeah. So loss function could be the entropy loss function, or different types of loss functions are there. So I'll not get into the details of it. There are different types of loss functions. So get that loss value, and they're also time stamped, basically, or sequence stamped, right? So likewise, if I do have n number of output nodes, then I'll have n number of loss values, individual loss values with reference to the time stamped output, right? So then what do I do with all these individual values? So I need to have one single L, basically. In order to back propagate that L and readjust these weights, I need to have one single L. What do I do that? Like take the average of all these individual L's, basically. So how do I take the average? Simply sum them. You get one L, big L, basically. So now this will be the total loss function value. So as far as this particular state of the network is concerned. So keep that as a reference and then back propagate. So back propagation is little different than that of the conventional MLP. We'll see how it is different and in what way it is different here. So in order to understand, as I said, what are those weight functions are, what are those states are, let's take up one simple example. So it's not a very complicated example. It's very simple to very simple, so that like it helps us to understand the network. That is the objective of this example. So let's take a simple task at first. So let's take a character level RNN. Let's not even go to word, sentence. We forget all that. So we'll only take a character level RNN. Why character? It's very easy to deal with these characters, unlike the real values. That's the reason. So it's very simple to demonstrate the network and it's working. Yeah. So take that word. Let's take only one single word, that is hello. So what does that contains? Basically, let's say I'll feed only 4 letters to the RNN network, and the objective of this network is, let's say, it has to predict like what would be the outcome post these 4 letters. Quite obviously, we know like it should be O, but how does a machine learn, basically? So let's try to make it learn, right? So that's what the objective is. So let's feed this HELL and try to predict that O. So let's then what is the vocabulary of this particular data? Vocabulary is only 4 letters, right? So that is H, E, L, and O. There are 2 repetitions of this L's for it. The vocabulary consists of only 4 characters. 4 characters. Now, the current state formula is all given as HT. Mind it, like we are in XT, basically. So correspondingly, we have the state HT. HT is all given by the function which is dependent on HT minus 1, that is the previous state, and the current input, that is XT. Right? So we know that like this is the equation for computing the HT. Then, so we know like how do we calculate that HT? if we expand that particular function, this turns out to be that WHH multiplied by h of t minus 1 plus WXH multiplied by XT, pass it through the nonlinear activation tan H, we get HT basically. So this is how we'll calculate. So then how do we calculate the output basically, recurrent neural net output, that is YT. So I've eliminated this cap like for just to make it simple, else it looks very cumbersome. So this is nothing but Y cap T. So estimated output YT, which is equal to WHY multiplied by HT. Now we do have WHH, we do have WXH, we do have WHY, and we do have XT, we do have HT, and we do have HT minus 1, and we do have YT cap, right? So these are the parameters that we have, and it's of our interest to understand the network architecture. It's as simple as that. So now, how do we build this network? There are different steps involved in the recurrent neural net. Let's try to find out one by one, like what are those steps that are there in the RNN. A single times step of the input is supplied to the network, that is XT. Whatever the current time I'm in is regarded as the T, right? That is called as XT, that is the input. We then calculate its current state, that is HT, right? So how do we calculate this HT? We calculate this by combining the input with reference to the previous state, right? That's how we'll combine and calculate the current state, that is HT. The current HT will become a previous state for next input. That this HT will become HT minus 1 for the next timestamp. Is that clear? Yeah. So now we can go on as many time steps as the problem demands. It all depends on the application. Whether I want to go 10 steps, or whether I want to go 100 samples, it all depends on the problem statement, application problem. Let's not worry about, let's take only one previous time state into consideration, because it makes our job easy of understanding. Yeah. So once all the time steps are completed, the final current state is used to calculate the output YT. We saw that from the equation. The output is then compared to the actual output, and the error is generated. Now use this error, then back propagate to the network, update the weights, and that is what we call it as the training of recurrent neural network is all about. Okay, so these are the simple steps that are there in the recurrent neural net. So even before dealing with the data, weights and other things, let's first we have to convert any symbolic data into the representational data. So one way of representing a symbolic data, which is of the form of text or character, is called one-hot encoded representation. So this you people might have come across if you people are working on deep learning algorithms. Even if not, it's very simple to understand. So as I said, our vocabulary consists of only 4 words, that is H, E, L, right? O is the one which we need to predict basically. So quite obviously, then I'll have 4 such symbols to represent. They're all binary symbols. So let me label these words basically in a one-hot encoded fashion. H corresponds to, H is the first vocabulary in our set. So if that is the case, let me give that value of 1 here. Then all other 3s are set as 0. Why? Because this is not E, this is not L, this is not O, right? So henceforth, all other 3 values are set as 0. So H is already labeled basically. So likewise, E correspondingly second bit is set, third bit is set, and third bit is set. If at all I'm expecting the outcome of the network as O, then the output should be 0, 0, 0, 1. Hope this is clear. It's very simple to understand. And this form of representation is called as one-hot encoding. Now let us take the weight matrices, right? After all, we are interested in these weight matrices and fine-tune them. How do we deal with that? Weight matrix is of certain dimension, that is 3 cross 4 here in this case, right? So take this weight matrix. This is nothing but our WXH. So this is the weight matrix which helps us connect the input to the hidden node. So let's say the size of this weight matrix is 3 cross 4, and all this matrix will have certain values, and they're all real values. But how would I initialize this value when I don't know anything, right? To begin with, I don't know anything. So generally speaking, these are initialized to some random values to begin with. Fine. So it has been initialized to some random values. So we have a WXH with this. Now, what do I do with this? So first of all, I need to do the matrix multiplication of WXH with reference to XT. So how do I do that matrix multiplication? Take that matrix WXH, multiply it with the first letter. Why? Because this is XT for me. Which becomes XT minus 1 for the next input. Though, of course, we are not bothered about XT minus 1. We are mostly bothered about HT minus 1. So do that matrix multiplication. We do get the H, right? That is these values basically, 0.28, 0.9, 0, 0.53. Post this multiplication of this matrix. Then step 2, let's go step by step. That is the first step, whatever we had noted down. Then let's go to the next step, that is step 2. Now moving to the recurrent neuron, we have WHH, right? The WHH itself with reference to the hidden node as the weight, which is a 1 cross 1 matrix, and the bias, which is also 1 cross 1 matrix. So generally speaking, we do tend to neglect this bias, but they are embedded in the equation. So for the letter H, the previous state, what would be the previous state as far as this H is concerned? We have not fed any input to the network so far. Henceforth, quite obviously, it has to be 0, 0, 0. The previous state is nothing but zeros, basically, right? So take those zeros, that is our HT minus 1, multiply it with WHH, be whatever the value. Since it is getting multiplied with zeros, we are left with nothing but the bias itself. If bias is 0.56, all that we get is 0.56, 0.56, 0.56. So this is step 2, right? This is step 2. Let's go to step 3. So what does that step 3 says? Now let me compute HT, right? So already we have calculated WHH. We know what is HT minus 1 is. You add them together with that of WXH into XT, pass it through the tanh. So already we have computed these two values. Simply add them, pass these values through the tanh, like it's a nonlinear activation. There we go, we get the HT. So this itself is nothing but our HT. So just by feeding H to the network, we are able to calculate the HT. So that H and this H is confusing. That H is the vocabulary H. This H is the state H. That's the difference. Don't get confused. Now, in order to eliminate the confusion of H, let's go to next one letter, that is E. So now, if I am there in the E, now this becomes XT. No more that previous H is the XT. Previous H is now XT minus 1. Hope that is clear. Yeah. The processed output HT now becomes HT minus 1. Whatever the HT we have calculated in the previous step now becomes HT minus 1. So take that HT minus 1, calculate this WHH, use the WXH and XT, right? This is what is desired. Now, if I want to calculate the current HT. So take the WHH basically, multiply it with HT minus 1 plus bias, will get these values, right? Similarly, WXH multiplied with XT. Note that weight matrix remains same. It has not been updated. When do you think these weight matrix gets updated? When do you think this weight matrix gets updated? Any guess? Weight matrices are same.
Back propagate.
Yeah. So right. So we have to back propagate and then update the weights. Till then, like they remain same. So this is the case. Like WXH, XT, HT minus 1 has been updated to the current state of XT. then similarly pass it through the tanh, we would have computed the HT. So now this would become HT minus 1 for the next state, and so forth and so on. You go on, like, basically. So this is what we've done. And this is how we calculate the output. We have passed only H, we have passed only E, and let's estimate the YT. So what would you expect, like, as far as the YT is concerned? What is the letter we are supposed to get as far as our word is concerned? If I fed H and E to the recurrent neural net, it is L, right? It is L. L is the letter what you're expecting as far as the prediction is concerned. So YT, let me just use the WHY, multiply it with the HT, we get this value. And you take these outputs, pass it through the softmax function. Softmax function does help convert these real values into probabilistic values, right? So class-wise probabilistic values. So we are deriving the class probabilities as an outcome of this softmax. So if we just look at that, so it gives 0.4, 0.19, 0.16, 0.22. Which one do you think the softmax has given as the expected output? Looking at those values.
H.
Yeah, so quite obviously it is H. So whereas the expected output was L. Yeah, expected output was the L, in place of which, like, we've got the H. So this is an error. Why do you think, like, the network is with full of error? Because as rightly said, yeah, we have not done the back propagation. So once we do that back propagation, the weight gets adapted and we get the right set of weights. So then we do the post multiplication of these weights in order to derive the right outputs or the right outcomes. And it need not be always 100%. There are certain errors that we need to live with. That's okay as far as the application is concerned. Yeah. So this is how these things would be learned using the back propagation. We can train the network using back propagation. So I'll not spend too much time on this again. Sorry, any doubts? Yeah.
Yes. Sir, the random installation of the H matrix, that is 3 cross 4. So the columns was 4, so the vocabulary size was 4, so columns will be 4. So how the row size will be dependent, sir? Like why 3, sir?
3. Again, it depends on the number of rows. I'll come to that. Like maybe to the end of this, we'll get to know what should be the row size and other things. While I deal with the TDNN, things will be clear. What should be the row size? What should be the column size? When we specifically come into the feature vector with reference to speech, things would be clear. Is that fine?
Yes, yes. Thank you.
Yeah, so I may take a little more time, sir. Yeah. That's okay, I suppose, till 1:30, if it's fine. Jagbandhu?
Yes, it is fine. We can go till 1:30.
Yeah,
start
yeah.
from 2:30.
Yeah. Yeah. Now, yeah. Okay. So suppose we had dealt with the characters. Now, how do I extend the same logic to, say, a number of words, basically? For example, these could be the set of input words that I'm feeding into the network. The cat, chase, the, basically, and expecting this network to predict something. Yeah, basically. So what it would predict. So generally speaking, quite obviously, the major probability would come to mouse. That's what cat does. The cat chases the mouse. So this is the expected output, target words, basically. So as soon as I feed the word the at xt, the network has predicted cat. So that is the y1 cap, like, basically. So then as soon as I feed cat to the network, already the network has predicted chased. So already when I feed the chased, then once I feed the, like it has predicted mouse, like, yeah. So this is how, and all these words are again one hot encoded, right? Depending on the vocabulary size, again, all these words will be one hot encoded. That's how we can handle the data. So these are the predicted outputs as far as this word level RNN is concerned. Now we have basically understood the fundamental architecture and weights, states, input, everything basically. Now, so how does the prediction happens? It's the same weights basically, WHH, WXH, WHY, similar to whatever we dealt. So for example, as I said, as soon as I feed the which is nothing but the XT, the YT cap would be the cat. So because cat would have the highest probabilistic output from the softmax function. Rest all other values will be minus 1.2, minus 0.8. So this is 1.7. Of course, here in this case, like it is 1.7. There, depending on the tuning of the network, like there could be different outputs as well. So likewise, the other way, other things as well. Yeah. So then again, multi-layered RNNs also comes into picture. So this is how complicated that multi-layered network is all about. Like, so not only that, like it's fed left to right, but it is also fed from bottom to top as well. The weights are shared basically, right? Yeah. So this is how that multi-layered RNNs look like. Yeah. So depending on the application and its complexity, we can adopt these many architectures based on whatever we are expecting. Yeah. So then apart from that, like we do have bidirectional RNNs as well. It need not be unidirectional. Whatever the network we dealt so far was all unidirectional. So there are bidirectional RNNs as well. So the temporal sequence is not only dealt from left to right, basically, they also can be from right to left as well. All right. So how do we handle such kind of data, or how do we increase the robustness of the system by introducing that back context as well? So this is where the bidirectional RNNs comes into picture. If we look at the network, this is how it looks. All the solid line do represent whatever we learned so far, and the dotted lines is the one which actually represents the other network. So in a sense, you take forward left to right network, then take the back network as well, which are all connected by the dots. Just stack them together on one top of the other, and arrow marks like are exactly inverse of the other thing. In a sense, the temporal sequence are navigated from right to left. Right, so rather than left to right. So both contexts are taken, and hopefully doing this exercise will give a better understanding of the data, right? So better understanding of the data and better sequential modeling aspects to this kind of network called as the bidirectional RNNs. And so forth, like is the deep bidirectional RNN. So then comes the backpropagation algorithm. So I'll not go in detail, but I'll just quickly take you through how do we use gradient descent in order to adjust the weights. I'll not go too much like into this. So if you know forward fully connected network backpropagation algorithm, we can just try to relate it to this aspect. There's a major difference between that backpropagation and to this one. We'll see what it is. So now, as I said, this is the forward pass. We saw that like already, this diagram. Now, how do I do that backward pass? Like, yeah. So take that L and back navigate, right? Back navigate in the same time sequential fashion. Start with L3, then go on to YT cap, and then go on to the node, and then go on to XT and do the left traversing. Right. After all, since I start here, like after all, I need to traverse left basically. So forward pass is all about left to right, and backward propagation or backward pass is all about right to left basically. So this is how I traverse as far as the backward propagation is concerned. This link was missing in the MLP. If you have noticed it, there was no such navigation. If you had noticed in that earlier case, like. Yeah. So this is how it looks. Like, as I said, each YT will give rise to ET, that is the error. So which is all represented as E0, E1, E2, E3, E4, whatever it is. So how do I do that back propagation? As we know, like we need to apply the we need to calculate the gradient of the error with reference to the parameters. And what are those parameters? It is all the weight parameters what I need to estimate. That's where this partial differentiation, the gradient comes into picture. So day by E by W basically, and sum all those weights with reference to ET. Why? Because it's not one T, because you would have navigated through many such errors, E0 to En, right? So summate all those values, basically you do get this W, and see, like if you have converged to certain result, if you've converged, you stop it, else you further keep on going and go on adjusting the weights. So that's in a very simplistic word, what do we mean by the gradient descent? That's how it works. Yeah, so this is where it is called as back propagation through time. So this back propagation is different than that of the back propagation, right? It is called as back propagation through time. Time is the notion by which like we adapt the weights. So let's say we do have states S1, S2, S3 with reference to T1, T2, T3, which are nothing but the timestamps, and WS, which is the weight matrix that is associated with reference to states, right? And it's a single matrix, WS, with reference to all states. So X1, X2, X3 are the inputs at times T1, T2, T3. So WX is the weight matrix associated with it. So now we get the outputs Y1, Y2, Y3. They're all capped basically at T1, T2, T3. So WY is the weight matrix associated with it. So then in that case, the back propagation works in this fashion. So ST, whichever the time state you are in, G1, which is the non-linear activation function. So WX into XT plus WS into ST minus 1, the previous state. Then pass it through again non-linear activation function. Note that G1 and G2 are not one and the same. Here generally we use tanh, here generally we use softmax. So WY into ST, we get YT. Let us now perform the back propagation for at least 3 timestamps. That gives a notion of how do I do for any n number basically. So ET is equal to DT minus this is the desired output at time t. That's what it means basically. Minus YT whole square. This is the error. So likewise, if I have to calculate E3, correspondingly D3 minus Y3 whole square is the error. So now start with the Y3 and then traverse back. That's how this adjustment of the weights happen. So if I do expand this particular equation, that is day by E3 with reference to WY, so I can just make it as day by E3 with reference to Y3 and Y3 with reference to WY. So E3 is a function of Y3. That's the reason there is this substitution. And we differentiate E3 with respect to Y3. That's the reason this equation has come. And Y3 is a function of WY. So that's where you're differentiating Y3 with reference to WY. So this is how you keep expanding this chain. So applying this chain rule, you calculate the error. This is what happens if you do expand with reference to E3 with reference to WS. So this is how the equation turns out to be a lengthy one. Now, if you just look at, notice this particular equation, there is one problem associated with this, which was generally not existing in the multi-layer perceptron or fully connected network. What do you think? If you just look at the mathematical expression. We have taken 3, that's fine. We have got these chain multiplications to do. What if if I had taken 100? What would be the nature of this product? It's huge numbers that you are multiplying, and let's assume all these values are less than 1. What happens if you keep on multiplying all fractional values?
Reduce to 0.
Yeah, so because your machine precision doesn't allow you have to represent beyond certain value, a small value, quite obviously this dies down, right? Yeah, this becomes 0, and they no way contribute to the network weight updates. So such a problem is called as the vanishing gradient. Likewise, if the weights are, let's say, greater than 1, what happens? Like, yeah, what happens to the multiplication?
Goes on increasing the value.
Yeah, so if you keep multiplying a value which is greater than 1, then it goes beyond the ability of what your machine can handle, right? Yeah, so it clips, and no more, like no value, and it's also unpredictable the way the machine behaves, right? It's unpredictable. So these are the two problems that we have as far as this kind of network is concerned, called as vanishing or exploding gradients, basically gradient problem. So how do I overcome this problem is where the LSTM comes into picture. Rather than blindly keeping all the timestamps like of the previous states, why don't I retain only the important one and do discard which is not so important one? So I've just told in a very simple one sentence, but there's a great deal of theory behind it. But I leave it to you people to study the LSTM, or if you people are BTechs, like certainly you would be opting deep learning as a course. So certainly you people can study that. Like, yeah. So that's the case. Like there is vanishing and exploding gradient problem. So general way of handling this exploding gradient problem is that there are different mechanisms. One way of handling is called as gradient clipping. So if you just check the value, and if it is beyond certain threshold, you just limit that value to that threshold. I mean, it's called as gradient clipping. Or altogether, like we can propose a different solution called as LSTMs. Here also we do have exploding gradient problem, which we do generally handle it by the gradient clipping, or any. There are a few more techniques to handle that. Yeah. So generally speaking, the internal architecture of the RNN looks like this. So here is the XT, here is the XT, and here is the previous state h of t minus 1, and this is the tan h. If you notice, they're not weighted. Any of these are not weighted or even gated, basically. So you just let as it comes. Like that is the problem. In a sense, you are giving equal weightage to all different things, like, right? So that's one of the inherent problems as far as this RNN is concerned. Rather, you do take up that network and modify it in a sense that you have certain dealings to do with that network. That's where this network becomes, this one neuron becomes quite complicated than that of a simple RNN. There's a sigma value, which is a nonlinear activation, and you have got a multiplication factor. Likewise, you have some additive factor over here, which contributes to this pipeline, basically. Yeah. So it's called as like yeah. Let's see. There are three major differences as far as this is concerned. The one thing is called as the cell state, which basically controls the information to flow from this point to this point. So if I can modify these weights, right? So that's the control that has been brought to the network node. So likewise, I can also forget about how much I need to remember from the previous state to the current state, right? So I need to forget also. So I can weight that, right? So I can learn these parameters. Then also, how much like I need to update to the next state, like selectively I can update the things as well. So these are, and also how much output should go out of this node, like, yeah. So these are some of the three different things. These are the three different changes that are brought to the plain vanilla RNN neuron to this particular structure. It has got a forget node, it has got a update node, it has got an output node. Playing around with the weights of these, we can control the working of these network, and that's what LSTM does. Okay. So fine, I'll stop at this point. So we've dealt with the RNN. I've not gone too much into LSTM. That's fine. As far as we know the fundamentals, it's always easy to learn the higher plane aspects of those algorithm. So I'll leave it at that. but let us try to spend some time understanding a basic architecture of another algorithm called as time delay neural nets. Time delay neural net. Yeah. So let's jot down the drawbacks of the RNN and LSTM. Recurrent neural network architectures have been shown they efficiently model all the temporal dependency aspects of be it data, be it acoustic data, speech, or whatever it is. It's highly efficient in maintaining those temporal aspects of it. The problem this RNN and LSTM has is due to its sequential nature of the network, training time is painfully slow. It's very slow. That is one thing, and the network architecture is such that we cannot parallelize the thing so much. Like, say we want to parallelly distribute the computation on our GPUs. There's a drawback as far as these networks are concerned. Of course, to an extent, we can do some sort of parallelization, but not to the extent like what we can do in case of MLP or a fully connected network. So feed-forward neural nets is one of the most efficient neural net as far as this parallelization is concerned. So that we are missing as far as this recurrent neural net or LSTM is concerned. That's one of the major drawbacks. Training time is too much, and we require high-end CPUs rather than very high-end GPUs. I mean, basically. So coming to alternate model. Why don't we, since feed-forward network is so good in terms of time, speed, so why don't we take that and modify it in such a fashion that it helps us to address that sequential information that it has been missed out with. So one such initiative was this time delay neural network. So let's try to understand the inability of most neural network architectures to deal properly with the dynamic nature of speech. That's one of the problem. Two important aspects, that is represent temporal relationships. That's not possible in case of feed-forward neural network. Then one more important problem with the feed-forward neural network is it doesn't learn the invariance as far as the time translation is concerned. So these are some of the inherent drawbacks of the feed-forward neural network. Why don't we take that and modify it in such a fashion it address all these problems or issues that are there, basically. So what is time translation? So it's very easy to make you understand with reference to image, let's say. So take an image. Let's say there is an object, let's say teddy bear, to the left top corner of the image. So you've given all those instances to the neural network, and soon in the test image, you just place the teddy bear from the left top corner to the bottom right corner. Let's say I've just simply placed that object to the right bottom corner of the image. So what do you expect the network to do? Do you think the network would still give me the output label as teddy bear or something else? At least I expect it to be giving as an label output as teddy bear, because hardly there is no change as far as the object is concerned, right? Object is same, but only the position has been shifted in the spatial coordinate. Likewise, in the speech, when I utter, say, stop voice consonant or voice stops, whatever be the sound units. So that stopping instant need not be precise, because after all, the biological organs are the one which are generating it, and based on the context, based on the event, so the timing events may change here and there. So that's nothing but the time shifting aspects of those features, right? So even if there is a time shifted features of those things, the network should be robust enough to identify or categorize those sound units into one of those classes that I'm intending to. Such thing is called as the translational invariance property. People who would have dealt with the filters do know like what is this translational invariance property is all about. So anyways, need not worry, I'll explain you what do we mean by that. Yeah. So for example, the specific movement of a formant in time is an really important cue, right? How do I capture those aspects? And it is irrelevant whether the same set of event occurs a little sooner or later. It could be that, right? That event may not be precise because we are not robots to utter the same sound units the same. Believe me, the sound unit what I utter now, nowhere in the life I would be able to utter the same thing if I want to utter that. So that's the uniqueness of the biological. So it has its own signature. Now, if such is the dynamics of the speech, how do I even capture the patterns inherent in those signals, right? So that's the challenge at hand. Any doubts? Yeah. So this time delay neural network is not something new that is introduced in the literature. In fact, the paper dates back to the year 1989. So IEEE transactions. Of course, there were a couple of papers from the same authors in other conference also, I suppose. But this is one of the most important paper that was proposed in the year 1989. They had proved that this time delay neural network was far superior. Was superior than hidden Markov model because machine learning algorithms dominated the scene till almost like 2010 to 2012. So post that 2010 to 12 is where the deep learning or neural networks have come into limelight basically. So thanks to Weibel and the co-authors, they are the one who actually proposed this time delay neural network. Let's try to understand what is this time delay neural network is all about and how it is so efficient in recognizing the speech. So that's what we'll try to understand. Yeah. So there are two very important properties as far as the time delay neural network is concerned. Hello.
Yeah,
Any
sir,
questions?
Sir, I just wanted to know.
Yeah.
We studied about RNN.
Uh-huh.
So what is the motivation of not using RNN and then going for TDNN? You explained from feed-forward network it is fine, but from RNN or LSTM to TDNN, so what is the key difference?
I'll discuss the TDNN. Once we discuss the TDNN architecture, we'll get to know what are the benefits of TDNN.
Sure.
Is that fine? Yeah.
Yeah, sure.
Yeah. Yeah. The basic two very important properties as far as this TDNN is concerned. It's a layered architecture as any neural network it is basically. So 3-layer arrangement. So let's take that 3-layer arrangement for our understanding. Else there is no limitation as far as the layers are concerned of simple computing units. In this paper, they had proposed the 3-layered architecture. That's the reason I'm keeping the 3-layer as it is in this. So a hierarchy can be constructed that allows for the formation of arbitrary non-linear decision surfaces. Of course, any number of layer stacking that helps us to classify the non-linear decision surfaces in the hyperplane that we know any network would do that. So the TDNN learns these decision surfaces automatically using error backpropagation. And it learns in a hierarchical fashion. Let's see what do we mean by that hierarchy. Yeah. Then one more important property of this TDNN is that the time delay arrangement enables the network to discover acoustic phonetic features and the temporal relationships between them independent of position. That is, their shift invariance property also has brought into the picture. So these are the two distinguishing features that we have as far as the TDNN is concerned. So the earlier paper, whatever in the 1987, they had demonstrated that the speaker dependent in the speaker dependent speech case, they had taken only 3 phones, that is b, d, g, and they had applied the HMM on top, and also they had applied this TDNN on top of the same data. They had demonstrated almost there was 5% accuracy jump as far as the TDNN is concerned. It's only that we from the community has to be blamed, because from the year 1987 to the year 2015, we never realized the potentiality of this network. We never brought, of course, there were few papers, but never we got into the limelight. Thanks to Vijayaditya Peddanti and Dan Povey, they did this and brought to the limelight. That's when this Kaldi came into limelight, basically. Of course, even before that, DNN HMM was there, but post this TDNN, easily it gives a big boost of performance. Yeah. So closer inspection reveals that a network invented well-known acoustic phonetic features. There is possibility even now to dig out those intermediate layers and pictorially represent what aspects of the data it is learning. It's quite possible, but someone has to take the pain. Yeah. So it also developed alternate internal representations to link different acoustic realizations to the same concept. So the same features are learned in different fashion. That's the beauty of this. So to be useful in speech recognition, a layered feed-forward neural network must have number of properties. What are those properties that are expected, which suits ASR? Should have multiple layers and sufficient interconnections between units in each of these layers. So without those interconnection, it cannot learn the notion of time, right? So let's see how do we modify this feed forward to make it learn the notion of time. Let's try to learn that. Should have the ability to represent relationships between events in time. So this is what we are trying to learn. Actual features or abstractions learned by network should be invariant. We know that, that is desired property. Learning procedure should not require temporal, precise temporal alignment. That is the thing, yeah. Because else, like, it becomes again one more step, right? We need to force align, and then again we need to generate very precise alignments, and then go on to train the network. So the network should not be dependent on these strict time alignments. Yeah, if we look at the structure, architecture that was proposed in that paper, this is how it looked. So generally, people who would have worked on audio and speech, we know what is a tap delay line filter is all about. All pass filtering and all other types of filters. They're all nothing but the delayed event filters, basically. So exactly, I think, though nobody has quoted, the same flavor is all drawn to the neural network also. So these are the features, that is U1 to UJ are the features. There are J number of feature vectors, basically of certain dimension. Each is of certain dimension. Yeah. So then feed that through different delays, basically. So if we look at this delay, this is 0. The delay is 0. Then it could be of some features, yeah, some frames, basically. D1. D2 up to Dn. So I can have such different delay elements over there in the network, pass it through the multiplier, which are nothing but the weight multiplications in our neural net. So likewise, you combine all of them, sum all of those values, pass it through the nonlinear activation function. Then we get the output. So this is as simple as that. So only difference being from that of the feed-forward networks, that we have introduced D1 to Dn as the delay elements. For the same feed-forward neural network, we have introduced the delay. So what it brings basically by introducing the delay? By introducing the delay, the same feature, what if it would have delayed by certain samples, certain time events, right? So that is what eventually you're training your network to be. So you're making your network robust to shift invariance. Is this clear? hope this point is clear.
Sir, can you repeat it again?
Yeah. So now we have these feature vectors, that is U1 to Uj. Let's say it's a MFCC feature vector. Still more nice representational diagrams are there in the subsequent slides. I'll show you. Don't worry. So this U1 is a feature vector of, let's say, 13 dimension or 39 dimension, which is a feature vector, right? So pass this feature vector and apply different delays for these feature vectors. Delay could be one frame, 2 frame, 3 frame, n number of frames basically. So subject them to different delays. The feature vector is not delayed at all in this case. Delayed by 1 frame, delayed by 2 frame, 3 frame, 4 frame, 5 frames, up to n number of frames. Then pass it through the weighted multiplication. Eventually, what you are trying to introduce to the network is how this feature would look like if it would have been a time delayed version of it. It's a very similar thing what we do in tap delay line filter. Right, in tap delay line filter, we introduce the delays to the filters. Right, so why do we introduce those delays? Because the filter has to learn different aspects of the time delays of the same samples, temporal samples. Whereas here, in place of temporal samples, I'm feeding the feature vectors. So the network learns what if a feature is delayed by certain amount, what if feature is not delayed. So it learns those aspects. So network become robust. Even that feature which was supposed to exist now has been delayed by 3 frames. Still those acoustic phonetic features are well encapsulated in these network. Is that clear?
Yes, sir. Thank you.
Yeah.
So wonder.
Yeah, please.
Sir, the number of delay units has to be the same for all the feature vectors, or it has to be different?
Yeah, so generally speaking, to make our job easier, we do maintain the same number of delay elements. But this n itself is variable. You got that point, right?
Sir, and the feature vectors all are fed into the input at a time, right, sir?
Yeah, this is U1, U2, U3 up to Uj. All feature vectors are fed one shot, like here in this case.
Thank you.
Yeah. So then a basic unit computes the weighted sum of its inputs and then passes this sum through a nonlinear activation function. It could be sigmoid, ReLU, or any of those things. The basic unit is modified by introducing the delays, that is D1 to Dn. In the basic paper, what they had proposed, these were the numbers. I'm taking the same numbers to make our understanding a little easier. The J inputs of such a unit now will be multiplied by several weights. We saw those weights. Weights are being multiplied for the delayed elements. Right? So what are those delay elements? N is equal to 1, we don't have any delay. It's as simple as feeding it to a feed forward network. Only delay happens from n equals 2 to, let's say we had totally 16 features, then J, if we had J equals 16, n equals 2 to whatever, like we are taking for each of those elements. So if we take n to be 3, capital N to be 3, and J is equal to 16, then essentially the whole network boils down to 48 different weights. So these are the parameters that essentially the network has to learn. So you can see that parameters is also not that costly as far as this network is concerned. Hardly only 48 weights that we have introduced by having 3 different delay elements for 16 feature vectors of certain dimension. Is that clear? Sorry, n is equal to 2. N is equal to not 3. Here in this case, it is n is equal to 2. So when I say n is equal to 2, there is a D0, D1, and D2. D0 is no delay at all. D1 is one frame delay. D2 is 2 frames delay. Is that clear? Yeah. So keeping that basic architecture as a flavor, in the year 2015, interspeech paper, thanks to Vijayaditya, as I said, and Daniel Pove, they proposed this time delay neural network, and they fine-tuned so nicely and brought it to the Kaldi framework. Soon there was a big jump in the ASR performance. Though today we speak about end-to-end network and all that, still believe me, the amount of data required to train this TDNN is quite low. The training time is also quite significantly low. And we ourselves have noticed, compared to end-to-end network, this Kaldi-based TDNN are highly suitable for real-time decoding. inferencing basically. It is still relevant even today. So nothing to discard as far as Kaldi is concerned. Yeah. So in a TDNN architecture, the initial transforms are, of course, it has to learn the transforms, right? W is all about learning the transform, are learned on narrow contexts, and the deeper layers processes the hidden activations from a wider temporal context. So I said, like, there is a hierarchical way of learning the temporal aspects of the data, which we'll see. If we look at the diagram, things will be very clear. So the higher layers have the ability to learn wider temporal relations. The lower layers will have smaller temporal relations to learn. When I say smaller, the very adjacent, the immediate next one frame, 2 frames. Whereas when I go up the hierarchy in the network, it learns the broader aspects of the time, right? So it's precisely like a convolutional neural network. What it does at the lower layers of the convolutional neural network, it learns the low-end features like edges and stuff like that. So as and on we move up the layer in the convolutional neural network, it starts grasping the abstractness of the given data. So for instance, if it is human face, it learns edges at the lowest layer as far as the filters are concerned. As the middle layers basically learns the eyes, nose, and those aspects. Still, the layers above, which are very close to the output layer, almost like it constructs the facial features of the humans. So that is the abstractness on which, like, the convolutional neural network progresses as far as the visual data is concerned. There it's with reference to the spatial data. Here it's with reference to the temporal data. Here the independent variable is time. There the independent variable is XY coordinate. I hope you understood the difference. Yeah, precisely that's what is being attempted in this network, whatever is being proposed in 2015. Don't worry, it looks cumbersome, but things are quite simple. These are the feature vectors. These are the feature vectors. And the current time state is all given by this top. So always we flow in this that is bottom to top hierarchy level. So this is the lowest layer, then subsequent, then subsequent, then subsequent. Then this is the output layer. Yeah, output layer has only one node, and that is the time instance of sample that we are interested in. That is the output sample. Yeah. So if we look at this, if we take 5 frames here in this case, combine those 5 frames in a weighted fashion, then go on to construct the intermediate hidden layer, that is T minus 11. Why T minus 13? If we just take this time temporal context, there are 13 frames to the left and 9 frames to the right. Why there is this skewed pattern? Why 9 to the right and why 13 to the left? Any reasons? Why it shouldn't have been T plus 13? Why? Because if we take too many frames to the right, it is nothing but the non-causal, and we are depending on the post frames. So it may not be much suitable for the real-time application. That's the reason we do take generally less number of frames to the right and large number of frames to the left. Hope this is clear. Yeah. Then they're all combined in this combination form, minus 2 to the left, plus 2 to the right. So likewise, different layers will have different. If this is the T stamp, like I'm considering, so minus 1 to the left and plus 2 frames to the right. So whereas if you just look at as and on I move to the higher and higher layers, the temporal context information being captured in the higher layers is increasing. So here I was only bothered about 2 frames to right and 2 frames to left. Whereas here already I'm talking about the 3rd frame to the right, right? So that's how the temporal context capturing of the information increases as and on I move to the topmost node. So here almost like you can say entire temporal information is all embedded in this particular one node. So that's how, as the layers progress, you tend to capture more time abstract information. So that's what it essentially does.
Sir, yeah. So in this, how will the weight be taken, sir? Like,
It's similar to whatever our feed forward network, right? They're all weights basically. All these arcs are weights. So then it's nothing but a feed forward network, but we are learning. Of course, I mean you can just partly say feed forward network and convolutional neural network. If you just take the combination of those two, it's as good as that. And all things are again learned using the backpropagation itself. It's the same vanilla backpropagation algorithm which we use in convolutional neural net and the feed forward neural net. The weights are adjusted.
Maybe could little bit variant, maybe they're not exactly backpropagation, something called backpropagation through time or something.
There is the time is all embedded in the layers, sir. Here.
That's right. That's right.
Yeah. And the way we have captured the information, right? Already the time is embedded, which was not there in the vanilla MLP or fully connected neural net.
That's
now we are building that hierarchy of the time dependency into the network.
Yes.
Hello.
Yeah, yeah.
Sir, here we are taking up to t+9, which are the advanced samples.
Correct.
And we are providing also the delay.
Hello.
So along with giving the advanced samples, we are providing the delay, and it reaches up to +2.
Sorry,
at the top.
Yeah.
From t+9 to it reaches up to +2. So if we take it t+7, say.
Here, t+7.
So will it be giving the means it will reach up to 0? And what it will be representing? I mean, I'm not able to formulate question. Basically, I'm asking that we are advancing and providing the delay as well.
So no, this is only with reference to the timestamps. This layer is only projecting you the timestamps. It's not talking about the delays basically.
Okay. Okay. Thank you.
Yeah, it's only with reference to this T. 9 post frames are taken and minus 13 frames are taken basically. I'll come to that. Okay. I know. So we'll just get exactly into how does this work. I'll demonstrate. Yeah. So in the next slides we do have. I'll cover that. Yeah. Yeah. So then not that like it stopped there in the year 1989. So TDNN belongs to a particular type of CNNs. Almost they boldly claim, couple of blogs and papers, they boldly claim it's nothing but a special case of CNNs. And so is the case practically also. Yeah, we'll see why is that reason. So that share weights along a single temporal dimension. Initially, TDNN models have been proposed for phoneme recognition task. That is 1989 paper. Later, they were applied for spoken word recognition in the year 1990, and also online handwriting recognition in the year 1991. So then TDNN allows the acoustic models to learn temporal dynamics of the speech signal using short-term acoustic feature vectors. So we'll see what those short-term feature vectors are. Recently, acoustic models with the TDNN topology have been shown to outperform the state-of-the-art DNN HMM. That is in the year 2015 and 16. So this is how it looks like basically. So for example, these are the acoustic features. It could be any of those features, right? It could be a spectrogram. It could be MLCC. So any of those could be those vectors. So it is a matrix again. It's no more one single sample that I'm feeding to the network. So it's a column vector stacked together. So if this is OT, so 17 to the left, it is OT minus 17, and OT plus 12 is 12 frames to the right. Yeah. So then layer 2, layer 3, layer 4, layer 5, and so forth and so on. This we have come across. So what does it say? So it shows an example of layer-wise context expansion scheme for a TDNN. Each frame of the higher level corresponds to a longer context than the lower layers. So that's evident from the architecture itself. So this hierarchical temporal context expansion is different from using of wide contextual window of acoustic feature vectors in the input layer. That's what we've been doing all this while. Yeah. So it has got multiple layers, and it generates the abstraction of the time notion into that. How this is how it's represented. For example, the first layer operates on the window of 5 frames. So then in that case, it is OT minus 2, OT minus 1, OT, OT plus 1, and OT plus 2. So these are the observation vectors that are considered for the first layer. So the same can be represented as minus 2, 2 plus 2, or simply as minus 2 to 2. That's what the paper, Vijay Aditya's paper deals with. This is the way I recommend you people to go through that paper. There's no point in me going through that paper and explaining you. You better read that paper. That's very, very useful. And these things will help you to understand that paper. Yeah. So fine. This is all. Yeah. There is something called as subsampling, if you've noticed or not, like, yeah, basically. So the frame connections that are used in TDNN after subsampling are shown in the figure, with solid lines. If you just go to that figure, all these dotted solid lines are post the subsampling. So there's a interleaving of these frames. He is not considering this. Subsampling is the one which actually helps improve the speed and also learn larger temporal context. Else, here also I would have taken all these samples to reconstruct. Why do you think like this subsampling is there, and what is the benefit if at all we need to have subsampling? What do you think?
We need not repeat the same information. So while passing it to the
generally speaking, if you take this feature vector and the corresponding the closest one, like let's say here in this case, closest one, somewhere it belongs here, right? Somewhere it belongs here, let's say. So there is no great deal of learning as far as the neural network is concerned, because hardly there would be any such dynamic changes between one frame to another frame. Rather than looking the immediate frame, why don't I hop on to the next few frames after, right? So that brings in a lot of temporal context into subsequent layer. Then you go on to next, like you just hop on to all together from here to here. Then if you go here and then go on subsequently, the higher layers would learn larger temporal contexts. Lower layers would learn narrow temporal contexts. That's the benefit. Hope that point is clear. Yeah.
I think that means locally as well as globally you are capturing information, I think.
Yes, no? Sir. Yes, sir. The local and also the global context is all taken into consideration while that network is learning that. Yeah. Yes. Yeah. So maybe I can stop at this point, or can I take 10 minutes? That's fine?
Please do.
Yeah. Okay. So now let us weave the TDNN as a 1D convolution problem. And it's exactly that. I mean, there's no exaggeration. It's exactly that. Yeah. So the TDNN is essentially a 1D convolutional neural network without pooling and dilations. If we know a neural network, a convolutional neural network architecture, we know what is pooling is. There's a max pooling, there's an average pooling. So then there are set of filters, then convolve all those filters with the image, basically, right? So that's what, it's a 2D convolution there. Yeah. Here also we do 2D convolution. I'll explain. But essential derivative of the 2D convolution is the 1D convolution. Yeah. So that's what it is. Yeah. The inputs to the network are the frames of acoustic features. Of course it is. Yeah. Right. The outputs of the TDNN are probability distribution, and what probability it has to learn. Last layer is again the output which gets passed through the softmax. Softmax will have number of classes. The number of classes depends on how many phones that I've initialized. It could be 30, it could be 40. So depending on the ASR that I'm building, depending on that, like I may have that many classes. So that is the goal, is to read the audio one frame at a time, basically. Read that one frame and put them into one of those classes. Who tells me which class it belongs to? Depending on the probabilistic output that I've got from the softmax. That tells me which phone it belongs to. So in one layer of the TDNN, each input frame is a column vector, right? That's what it is, yeah, because feature vectors. A single time step in the signal. It is xt what I'm talking about, with the rows representing the feature values. Of course, rows are the one which actually represents the feature values. How? I'll tell you that later. So the network uses a smaller matrix of weights, that is the filters basically, which slides over this signal and transforms it into an output using convolutional operation. I'll pictorially show you how this happens. Things becomes easier to understand. Especially people who have dealt with signal processing can easily understand these concepts: kernel, filter, convolution. We know day to day we play around with it. So weaving TDNN as a 1D convolution, let's say. So here we have three different colors. One is the light blue, one is the dark blue, one is the green, right? So what do these represent? So these light blue is nothing but the feature matrix. It has got rows and columns. Each one column is nothing but the time frame, xt, right? Xt, and it has got certain dimension. It could be 13, it could be 39, whatever it is. Now we have taken 3 because it's easy to understand for us. Now take a weight matrix which is dark blue, place it on the light blue, do the product sum, yeah, sum of products basically, yeah. Sum of products, which is nothing but the convolution operation, and shifting is inherently there. A convolution contains the shifting, and it gives rise to one such sample, right? So likewise, shift it, do the same operation, you get the second sample. Shift it, do the same operation, you get the third sample. This is precisely what happens in the TDNN also. So how do we mathematically define this? Let's assume that we have input vector xt belonging to a m-dimensional feature vector, which is generally 13, 39, whatever it is. Yeah, xt contains some numbers in it, such as the amplitude. So that's what generally the feature vectors are. X-axis is the frequency, y-axis is the magnitude or amplitude. So that's what the feature vectors defines. So we collect these vectors into a matrix where each vector represents one time step t of our speech signal. One sample taken every 10 milliseconds or 20 milliseconds, depends here. So this is how it looks. Already Samudra Vijay sir has extensively dealt on that, but this is the spectrogram. Likewise, we can also construct a color mapped plot of a MFCC also. This is how it looks. So there are formant information which are embedded in it. Now take such feature vectors and feed it to the TDNN. That's what we are supposed to do. It does applies the 2D convolution on top of this and generates the output. How it does, yeah. Observing the input over time, we then have a matrix of input feature vector x. Sorry, any doubts? Yeah. So and that matrix is of size m cross t. So Jeevan, now hope you got the how many rows and columns should be there in the matrix.
Yes.
Yeah. So then W belongs to the real value, that is m cross L, basically m cross L, which is nothing but the filter itself. Weight matrix is nothing but the filter itself. Yeah. So where the kernel has the same height of m and a width of L. Hope you got that now. L is anything, but m should be dependent on the dimension. Is that clear?
Yes.
Yeah. So this is the m is this is the height, this is the width, right? So and it need not be always square. It could be anything also, but preferably square, because computation becomes easy for us to handle. That's the reason why they maintain it to be square. That's the only reason.
Like the JPEG comparisons. How is it?
There also we do blocking, right? So 8 cross 8. So take that 8 cross 8, pass it through the DCT, and neglect all the coefficients and only retain few coefficients to reconstruct the data. I mean, similar operations are also performed here in this case as well. Yeah. Okay. So then this is the entire T axis. Then we do generate the O output. Yeah. So the kernel W slides over the input signal with a stride of S. There's a stride factor. If you know CNN, we know what is stride. If I shift by one sample, one shift sample of that convolution mask or W, we do say that stride is equal to 1. If we do shift it by 2, then stride is equal to 2. Hope that is clear. And also we do perform zero padding. We do this zero padding because convolution operation actually reduces the size of the output. In order to avoid that, we do that zero padding. Let's assume that P is equal to 0. We are not zero padding anything. And for simplicity, let us keep that S equals 1. So it makes our job easy to understand. Then the output vector is given by this relationship, output size, basically. So this is the floor indicator, floor function indicator. Yeah. So then at each time step t, the TDNN performs the convolution operation. We saw what is the convolution. Convolution is nothing but the element-wise multiplication, which is nothing but the Hadamard product of the kernel weights over the input beneath it and sums those multiples. It's a sum of products, basically. So then the thing is, whatever that multiplied version is all passed through the nonlinear activation function, which could be sigmoid, ReLU, whatever it is. Yeah. Or even it could be P norm, right? Norm is also a nonlinear operation. Yeah. So this forms the output. It generates an output which is ZQ, which belongs to Z. So which is the entire output set, vector set, basically. Yeah, right. So the light green vector that itself is nothing but the Z. Yeah. So this ZQ is all given by the sigmoidal operation, nonlinear activation function, W multiplied by the XQ. XQ is the input feature vector, right? So W is the weight matrix. Then there is a bias. It's the same operation what we dealt in the earlier networks also. Now, if you do tend to this star is the convolution operation. Now it's a 2D convolution. It's not a single dimensional convolution, right? It has got M and L. So henceforth is a 2D convolution. It's exactly what you do on the image. That's the precise equation. Yeah. So that's what they in that 1989 paper projected this particular thing. So here time axis is there. Here is the frequency axis is there, which is nothing but the spectrogram. So take such 3 frames, I think, 3 frames. Do that delayed a summation. Then you generate the hidden layers. So hidden layers, I think there are 8 such filters. So why the depth of that? Yeah, this is the depth basically. The depth generally denotes the number of filters you're using. More number of filters, more number of features it learns. 8 is this depth. And there is also width for the next hidden layer also. Here there is no subsampling. They have not used it in that earlier paper. So subsampling was the concept introduced by Vijayaditya Pedindi's paper because to reduce the computation. Else, this also is hugely competitive. And then again, get into the hidden layer 2. Here we have got 3 filters. Then add them, sum them together row wise. You get the probabilistic value of the ba, da, ga. Then whichever gives the highest, you categorize that particular frame to be of that particular phoneme. Hope this concept is clear. Right. So that's what I've described here also. Then the representation of the convolution matrix, we can convert this into a sparse matrix. How do I convert this into a sparse matrix? This is how we do. So take that input feature vector, then unroll it, stack them together in the column in the form of a column vector. Convert that weight matrix to a sparse weight matrix. Do multiply these two, and that is the operation. That is the convolution operation. This is the expected operation, and this is what we can highly efficiently do on our GPUs. That's the reason why Kaldi training is much faster than any end-to-end network. And we are not feeding the raw input samples. We are feeding the feature vectors. So with that, I'll end my session. Sorry, I've extended more than half an hour, 40 minutes. Any doubts? Yeah, bidirectional RNNs. Yeah, Paliwal. Sir, any questions? Any questions you have? Yeah. So then keeping this as a sir. Yeah. Please.
Sir, one thing just I did not understand, sir, the need for the delay. Like, what role does it play?
So if I see whatever the notion of the time delays are essentially imbibed in the way we have chosen the frames basically. So you took the current frame, the time delay version of it. It's to create the shift invariance aspect to the neural network. If you don't delay that, it doesn't learn the temporal shift invariance aspect to the network. So in a sense, you take the samples, let's say a feature vector belonging to vowel A. So if you just feed that vowel R to the network, it only learns that aspect, right? So if you take the same R and delay it with certain time, so then this neural network learns the aspect of the delayed version of the phoneme R, if it is with reference to one single frame. So even if it is delayed in some training, in testing data, the neural network understands still that is a phoneme A, though it has been shifted by certain time. You got this, right?
Yes, sir. Sir, like, is it similar to the masking in BERT?
Masking in no, I'm not privy to that BERT masking. So I don't know. I don't know if it is the similar concept. What I'm saying.
Thank you.
Peaking rate variations, for example.
Yeah, correct. Speaking rate variation, and the same I can utter for 4 or 5 frames that could become 1 or 2 frames for some other speaker. So they're all a time stretched concept of the same sound unit. So generally speaking, we are enabling this network to learn all those concepts. Yeah.
So one doubt. So in TDN, as we go up from higher feature vector to lower feature vector, where you went from t minus 13 to t plus 9 to just one block as t. So you're compressing the information of all the t minus 13 to 3 plus 10, like almost
Correct,
22 feature information you're compressing into a single information.
Correct. So it's the abstractness. You go more and more higher layers. You are learning more and more larger temporal aspects to the network. Yeah.
Oh, okay. Thanks.
Yeah. So any other questions? Yeah. If there are no questions, I think.
Sir,
Yeah.
Sir, in TDNN, why we generally give high resolution features? I mean, why we stack with all other things? I mean, UBM, JBM. I mean, we extract high vectors, right? And then we feed it. Why can't we directly feed only MFCC? When I mean, it is capturing more or less the long-term dependencies also, right? I mean, the temporal dependencies.
Yeah, so on top, like it is all the experimentation, some unique combination has given the best result. So that's what the literature says. And once the literature says this is the best combination of performance I'm getting, so we do take it and blindly follow, right? So as long as somebody comes up with the better configuration, still it is doable. I'm sure, like if we fine tweak this TDNN, still it may give better results in some cases and some scenarios, but people have to take up and work on that. So somebody has given that flavor and they've said like this is the best combination to get the result, so we've been using that combination. Yeah.
Okay, sir. Thank you.
Yeah. If there are no questions, I think I'll stop the session here because people have to go to lunch and come back for practical sessions. So you people will be running Kaldi model on Google Cloud server. So take it in that stride, and even if you go back home or to your institutes, still you should be able to access the resources from cloud and still be able to run that. Yeah. So then you learn the concept of building, because it's not possible for anyone to go and teach you every minute details of the Kaldi, and it's a ever-ending process, right? So as in on, you keep investing time on that, you get to know more and more details about the practical implementation aspects. So you need to spend more time on that. So generally speaking, so what this workshop is meant for is, you should be able to take the data, build the system, and be able to build the system independently at your institutes. So that's the whole purpose. So we have created 11 different instances. I think that many physical resources can be accessed. Only binding is, as a group, like you people have to share the resource and learn. So at least one or two people will get the chance of working. Others may observe. And if you have any questions within the group, you can stop. You can prod. Like basically, that's how you can learn. And always we do provide all the materials, be it PPTs, the installation aspects, and all other details will be provided from us. So it's like one group will have one access to code the thing and build the system. Others can observe it, because we cannot take 80 GPUs. It's very costly thing. Yeah. So that's the reason you get one instance per one group, whatever we made. 11 to 12 accounts will be there. Shanti. Yeah.
Yeah, Deepak bhaiya, what I have a I can access Google Cloud for myself. So is the computer actually I created a compute engine instance, but I do not know how to configure GPU, and also I went only for CPU, but I can also go for the other GPU. So is the course, when we enter the course, are we going to directly enter into a created instance already? Or
No. We'll let you know how to create the instance.
Okay.
Yeah, we'll do that. Like, yeah. So it's a complete exercise. Yeah.
Okay.
So
thank you.
Only problem is if you have your own accounts. We struggled to get the GPUs for us for this workshop. So we went to the highest level in the Google, then we got the GPU resource, because GPU resource is highly in demand in the market. So of course we can create the Google Cloud account. We get $300 worth free credits, but there's no guarantee that we may or may not get the GPUs. But we can give a shot. If we don't get the GPUs over there in your account, you can switch to this account and still work on it.
Okay.
Yeah.
Thank you.
Okay. Yeah. Fine.
Hi.
Hello. Yeah.
Can I ask a question?
Please, sir. Please.
We at CIL, we procured one GPU recently, and that is a 48 GB GPU we purchased, and we have deployed it on an Ubuntu system. Because we cannot go to any cloud system, so we were thinking that we can use our own internal resources. Do you think that would be fair enough to get us started?
That's good enough, but only thing is, now we are all the tools necessary, right? Like be it Kubernetes, everything, a CUDA, certain specific version, Ubuntu specific version. So there are many dependencies as far as the running of ASR is concerned. That may be true as far as your Kaldi is concerned. Still, you can go ahead and run. That may not be a big challenge. But when it comes to wave to wave, it's a highly complex package, basically. So it is dependent on so many softwares and versions. Whereas if it is on the cloud, it's easy to control for us and help you to come out of the problem. Whereas once you're stuck in your local loop, right? We getting into your local loop and helping out to come with the problem may become little difficult for us. Yeah. First of all, we are conducting this online. On top, like that's the challenge we have. Yeah.
Okay. Good.
Yeah. Yes, sir. Yes, sir. Yeah, if there are no questions, then we can take a break. Let's have lunch. Then let's meet for the workshop. Yeah, please, sir. Surya, sir. Yeah. Surya, sir.
No, I did not ask anything, Deepak.
Okay, okay. You raised a hand. That's the.
Oh, maybe by mistake.
Okay, okay. Yes, yes, sir. Yes, sir.
Jagabandhu, do we meet at 2:30 now?
Maybe 2:45.
Yes, please. Please tell the announce the
Yeah.
time. Thank you.
Yeah, I think 2:45 is good enough. Yeah, for us to meet. Yeah. Okay, we shall meet at 2:45. Thank you. Thank you all.